Dear students, in this section we will learn how light exerts force on a surface and how the electromagnetic wave exerts pressure on a surface on which it incident. Before moving to radiation pressure, it will be must for us to learn about photons. So let us first learn what is photon. The concept of photon and quanta come from the quantum mechanics and quantum theory. Quantum mechanics is a mathematical model that describes the behavior of a particle on atomic and subatomic scale. It demonstrates that matter and energy are quantized or come in small discrete bundles. So, first point about the photon, we can say photon can be considered as a particle of electromagnetic radiation and it is defined as a discrete bundle or quantum of electromagnetic energy, right. Let us learn what is the meaning of quantum. The term quantum is the smallest elemental unit of a quantity. It may be any quantity, or you can say smallest discrete amount of something. Okay, so let us move to the second point about the photon. A photon describes the particle property of electromagnetic wave instead of overall wave itself, right. In other words, we can say we can picturize an electromagnetic wave as being made of individual particle and these individual particles guard the photon. Okay. The modern photon concept was developed by Albert Einstein to explain the photoelectric effect, in which he proposed the existence of discrete energy packet during the transmission of the light. The third point about the photon is light exhibit the wave property under condition of the refraction and interference and particle property under the condition of emission and absorption of the light, right. These are three important properties about the photon. And one very important property about the photon, according to the photon theory of the light, the photon behave as a particle and wave both as we discussed, and it move with a constant velocity that is equal to 2.9979 into 10 to the power 8 meter per second. This is nothing but speed of the light and in empty space. Okay. So, these are some points about the photons. Now, let us discuss some basic properties of the photons. In those properties, we will cover energy and momentum of the photon. So, let us learn basic property of the photon. The energy of each quantum of light depend on the frequency of the light. That means energy of a photon depends on the frequency of the radiation, that is the electromagnetic radiation. In particular, the energy of photon equals Planck constant multiplication frequency of radiation, or mathematically you can write E is the energy of the photon, E equal to H multiplication F, and we know F is the frequency and it can be written as C divided by lambda. This is the energy of a photon, right. Photon is massless. Its rest mass is 0 because photon is always in motion in empty space. It is massless, but it is having the momentum. Its momentum is equal to energy divided by velocity of the light, right. And it is related with the expression P equal to E divided by C. E is the energy of a photon and C is the velocity of the light. And here we can substitute the value of E equal to SC divided by lambda, and C will get cancelled. We will have the term H divided by lambda. This is the momentum of the photon. Okay. And one very important property of the photon, that it can be destroyed or created when radiation is absorbed or emitted, right. This is the very important property of the photon. We will discuss this property in the photoelectric effect. Okay. When photon interact with other object, the energy and momentum are transferred, and it is transferred in such a way it is equivalent to the interaction of two classical particle. That means the interaction of the photon with any other matter can be treated as a classically. So, while treating the momentum equation or energy equation, we will treat energy equation in the classical case or momentum equation in the classical case. Okay. So, these are very important properties of the photons. Now, let us learn how to solve the problem of the photons and how to find the energy of the photon. There is some calculation trick through which we can calculate the energy of the photon in faster way. So, let us take first illustration. In this illustration, it is given what is the energy in electron volt of a photon of wavelength 12400 angstrom. In this illustration, we need to calculate energy in electron volt. Electron volt is a unit of energy, that is very small unit. Generally, we calculate the energy of a photon in electron volt. If we want to convert this energy into joule, we multiply with a factor that is equal to 1.6 into 10 to the power minus 19. Okay. So, we know the expression for the energy of a photon. We can write E equal to HF or HC divided by lambda, right. We know H is a Planck constant, C is a velocity of the light. H is universal constant, that is always fixed value. C is also velocity of the light, it is also the fixed value. That means for calculating the energy of a photon, every time we need to multiply H and C, which will always remain constant. That means for calculating this part, we need not to multiply H and C every time. We can use a ready-made calculation to avoid calculation steps, which can save our time and effort. So, we can write E equal to, that is equal to 12400 divided by lambda in angstrom. That means, if we substitute the value of lambda in angstrom, we will get the energy of a photon in electron volt. And here in our question, the wavelength is given as 12400 angstrom. So, let us substitute this value and this is equal to 1 electron volt. That means, the energy of the photon equal to 1 electron volt. Let us move to the next illustration. In this illustration, it is given how many photons of radiation of wavelength lambda equal to 5 into 10 to the power minus 7 meter must fall per second of a blackened plate in order to produce a force of 6.62 into 10 to the power minus 5 Newton, right. And here you can observe we need to calculate number of the photon of radiation and wavelength is given, and this force we need to develop due to radiation, right. And we know from Newton's second law, rate of change of linear momentum equal to force, and we know photon, the interaction of the photon with any matter can be treated as classically. So, here first of all, let us calculate the momentum of a photon, and we know the formula, right. And second part of the question, it is given at what rate will the temperature of the plate rise if the mass of this plate is 19.84 kg and specific heat equal to 2500 joule per kg Kelvin. So, let us move to the first part of the question. This is the first part of the question. As we are discussing, let us write the momentum of the photon, because we can treat the interaction of the photon with any matter classically. So, momentum of the photon is given by h divided by lambda. This is the momentum of a single photon. Let us assume the number of the photons falling on the plate per second. Let us consider this quantity as n, small n. And if we multiply small n with this quantity, that is the linear momentum of a photon, we will get the momentum incident per second on the plate. So, n is the number of the photons falling per second on the plate, and this is the value of the linear momentum incident on the plate per second, that is nh divided by lambda. Because this plate is blackened, That means it is absorbing all of the radiation. That means the final momentum of the photon equal to 0. That means we can find the rate of change of the linear momentum. That means delta p by delta t equal to nh divided by lambda minus 0, that is the magnitude. So, we can write delta p by delta t equal to nh divided by lambda, right. And we know this quantity, that is delta p by delta t, is nothing but it is the force by the definition of Newton's second law. So, we can write F equal to delta p by delta t, that is finally equal to nh divided by lambda, right. And from this relation we can find the value of n. N is equal to lambda f divided by h, right. Now, we can substitute the given value. We are given capital F, that is 1.62 into 10 to the power minus 5, and lambda is equal to 5 into 10 to the power minus 7 meter, and h, this value is always constant. It is having the value 6.62 into 10 to the power minus 34. So, after calculation we will get the value, it is equal to 5 into 10 to the power 22. This is the value of small n, that is the number of the photons incident on the plate per second. Let us move to the second part of the question. This is the second part of the question. At what rate the temperature of the plate rise if mass of the plate is 19.84 kg and specific heat is equal to 2500 joule per kg Kelvin. Let us write the value of small n. Small n equal to 5 into 10 to the power 22, right. And we know energy of a photon, energy of each photon, that is equal to St divided by lambda, right. And we know number of the photons incident on the surface per second. That means, if we multiply this number with the energy of each photon, we can calculate the total energy incident on the plate per second. That is the total energy absorbed by the plate in 1 second, right. So, let us multiply this quantity with n, right, and we know this is a ready-made formula. We can write Sc equal to 12400 divided by lambda, and while using this formula we should substitute the value of lambda in angstrom. We know the value of n, we know the value of lambda, we can substitute, we will get the energy in electron volt, right. This is in electron volt. We can convert this calculation into joule. How to calculate it? We need to multiply this relation with 1.6 into 10 to the power minus 19. So, this is in electron volt per second, and if we multiply this after calculation is equal to 19840 joule per second. That means, this much of energy, this joule of the energy per second incident on the plate per second. Plate is absorbing this energy. That means, its temperature will keep on increasing. Suppose it is absorbing energy dq in dt time, and during this process its temperature increase by d capital T. So, here we can write dq equal to mc dt. We can find the rate of absorption, that is the rate of energy absorbed by the plate, that is equal to dq by dt, and dq by dt is equal to mc dt by dt, right. dt by dt means this is the temperature and this is the time, that is the rate of increase of the temperature with respect to time. And here in the question we need to calculate this rate. So, we can write dt by dt equal to this value, right. This is the value of energy absorbed by the plate per second we have calculated. So, let us calculate now this divided by mc, and here m is 19.84 kg and c is given 2500 joule kg per Kelvin. So, this is the value after substitution, and after calculation we get the value of dt by dt as 0.4 Kelvin per second. This is the rate at which temperature of the plate will increase. Let us take one more illustration. In this illustration, it is given a 100-watt point source emit monochromatic light of wavelength 6000 angstrom. Calculate number 1, the total number of the photon emitted by the source per second, and second part of the question is the photon flux at a distance 5 meter from the source, and we are given the value of small s, that is the Planck constant, and velocity of the light, right. In second part, here you can observe it is given photon flux. Photon flux means number of the photons incident on the surface per unit area per unit time. That is intensity of the photon we need to calculate at a distance 5 meter from the source. So let us move to the first part of the question, that is the total number of the photon incident by the source per second, right. For this purpose, we need to calculate the energy of a photon of wavelength lambda, lambda equal to 6000 angstrom. So let us write the formula. This is equal to Sc divided by lambda, and we know H multiplication C, this is always a fixed value, and here for calculating the energy of a photon we use a ready-made formula which save our time. So here we can write E equal to 12400 divided by lambda, and lambda here should be in angstrom. The value will be in electron volt. So let us substitute the value, lambda equal to 6000 angstrom. So after calculation, this is equal to 12400 divided by 6000, but it is in electron volt. And if you want to convert this value to joule, we need to multiply this quantity with the quantity 1.6 into 10 to the power minus 19, right. And here we can calculate, and this value is equal to 3.3 into 10 to the power minus 19 joule. This is a energy of a photon, right. Now let us consider total number of the photon emitted per second, and let us consider this value as a small n. So small n is the number of the photon emitted per second. If we multiply this E with n, we can calculate the value of the total energy incident per second, or you can say total energy emitted by source per second. So En equal to energy divided by time, and this is nothing but power. Now we can rearrange this relation. We can find the value of N equal to power divided by E, and we are given the power value 100 watt, and E equal to in joule 3.3 into 10 to the power minus 19 joule, and this after calculation it is equal to 3 into 10 to the power 20 photons per second. So this is the first part of the question. Now let us move to the next part of the question. In next part of the question, we need to calculate the photon flux at a distance 5 meter from the source. That means we need to calculate the intensity of the photon. For calculating this intensity of the photon, we need to calculate the intensity of the radiation at a distance 5 meter from the source. And we know the power of the source equal to 100 watt. So let us calculate the intensity at a distance 5 meter. Because this is a point source, we can imagine this energy is distributed in all sides. That means the sphere of radius 5 meter. So for calculating the intensity, we need to divide this term, that is the power, to the value 4 pi r square. 4 pi r square is nothing but the surface area of the sphere center at the source. Source is at the center, and surface of the 5 meter sphere represent the uniform intensity due to this point source. So this is the intensity P divided by 4 pi r square, and here we can substitute P equal to 100 and this r equal to 5 meter, and this is equal to 100 divided by 4 pi 5 square. So after calculation, this is 25 multiplied by 400, and this is 1 divided by pi watt per meter square. This is the intensity of the radiation at a distance 5 meter, right. Now we can calculate the number of the photons passing normally per unit area. This is the energy per unit time and this is the area. That means this is the energy per unit time per unit area. That means if we divide this term, that is the intensity of the radiation, with the energy of a photon, we can find this value, that is the number of the photons passing normally per unit area per second. That is I divided by E. E is the energy of a photon. So let us divide I with E, and we know the value of I, this one, and E we have calculated, that is equal to 3.33 into 10 to the power minus 19. So this is equal to 10 to the power 18 photon per meter square per second. This is the photon flux. It is also called the intensity of a photon on given surface. Okay. Up to this point we learn about photon. Let us now discuss about radiation pressure. While calculation of the radiation pressure, one term is very common, that is the energy, flux and intensity of the radiation. So let us first discuss about intensity of the radiation, that is what is the meaning of intensity of radiation. Intensity of the radiation is the energy crossing unit area per unit time, right. This is the intensity of the radiation. You can observe here energy crossing per unit time is nothing but power. That means it is also the power crossing unit area, and this term is also called the energy flux. So now it is clear about the energy flux or intensity of the radiation. Now we can frequently use this term, that is the intensity of the radiation. So let us now develop the definition of the radiation pressure or expression for the radiation pressure. Let us consider a beam of light having intensity capital I incident on a surface having area capital A, right. So let us take a area capital A on which radiation of intensity I is incident. You can observe here the area vector of this surface. Direction of the area vector is toward the position of the observer. Suppose position of the observer is at the position of my pen. So you can observe here the angle between the area vector and direction of the motion of the photon is 0 degree. That means you can say the photon direction, ray direction and area vector both are in the same direction, that is the 0 degree. In this case we can find the power incident on the surface, because intensity is the power crossing unit area. That means if we multiply capital I with area, we can find the value of power. So this is the power incident on this surface. This is I multiplied by A. Okay. Suppose we turn the orientation of the disk. Suppose if we make the orientation of the area vector perpendicular to the intensity direction or ray direction, you can say no radiation will cross the surface. In that case, you can say power crossing the surface will be 0. That means if you incline the surface with respect to direction of the photon motion, or you can say in the direction of the ray traveling, the power will decrease. That means at angle 90 degree no power, at angle 0 degree there is maximum power. That means we can relate this intensity and capital A with the trigonometrical term, that is cos theta. So let us make one situation where the radiation incident on the surface at certain angle. This angle is theta. So here we can find the power P equal to IA multiplication cos theta. Theta is the angle between the ray direction and area vector direction. This is okay. You might have learned this formula while calculating the flux. If we calculate the electric flux, then the electric flux phi is equal to E multiplied by A multiplied by cos theta. E is the direction of the electric field lines or electric field vector, and A is the direction of the area vector, and theta was the angle between the electric field vector and area vector. So, you can use this formula, that is the P equal to IA cos theta when ray are incident at certain angle with the surface. Okay. So, we got the power value, and we know linear momentum of the photon, that is small p equal to energy divided by velocity of the photon. So, we can write linear momentum of the photon p equal to E divided by c. From this expression, we can find the linear momentum incident per unit time. If we divide p with time, we can find the linear momentum incident to the surface per unit time. That is p divided by t equal to E divided by c and overall divided by t. And you know, this E divided by t is nothing but power. We can write E divided by t, and this is multiplication c, and this E divided by c is power. So, this is power divided by c, right. So, this is the linear momentum incident on the surface number 1, that is the left surface, right. Suppose rays are incident on the surface at certain angle. What we need to do? We need to substitute the value of P, that is equal to IA cos theta in this expression. And here, for the simple relation, that the first case, we can write IA divided by C. So, we can write this relation IA divided by C, and for this particular case, this is IA cos theta divided by C, right. This is the linear momentum incident per unit time. Now, let us consider two cases. Two cases are possible here. One case is, suppose the surface on which the radiation is incidenting is perfectly reflecting. That means the radiation incident on the surface completely reflected back. So, let us make the diagram of the situation, and here the situation is surface is perfectly reflecting, right. So, let us calculate the linear momentum change. This is the incident radiation, and reflected radiation will return back like this. Okay. So, here we can find the change in linear momentum. Suppose if we take the rightward direction as positive, so final linear momentum will have the same magnitude, but in the opposite direction. We can find the magnitude of change of linear momentum. This was P divided by T. So, here we can write delta P divided by delta T equal to initial is IA divided by C, final is minus IA divided by C. That means, we can write delta P divided by delta T equal to 2 IA divided by C, right. You know, force definition, that is rate of change of linear momentum. So, we can say this is the force exerted by radiation or beam of light on the surface, right. This is the radiation force. We got the value of radiation force, which is normal to the surface. So, we can find the radiation pressure. Radiation pressure will be nothing but force divided by area of the surface. That means, IA divided by C and overall divided by A, that A and A will get cancelled. That means, the radiation pressure should be 2I divided by C. This is the radiation pressure, right. Now, let us consider what happens when light radiation incident on the perfectly black surface, that is perfectly absorbing surface. So, let us make the diagrammatical situation. The incident radiation is like this. This is the incident radiation, and 100% radiation was absorbed now. So, no radiation will reflect back. This is the absorbed radiation. That means, initial linear momentum is that was equal to I divided by C, and you can observe here final linear momentum equal to 0, right. Initial linear momentum we have calculated, that is power divided by C, not I divided by C, that is power divided by C, and final linear momentum was 0. You can observe here. So, here we have calculated initially the incident radiation, that is the incident linear momentum on the surface per unit time, that is P divided by C or IA divided by C, and final will be 0. That means, change in linear momentum during this situation is equal to delta P by delta T equal to IA divided by C, right? And this is nothing but force exerted by beam on the surface. So, here we got the force which is in the normal direction. From this expression we can find the radiation pressure. Radiation pressure will be equal to force divided by area. So, we can write radiation pressure P equal to F divided by A, and this is nothing but I divided by C, because A and A will get cancelled, right. So, this is the situation when surface is perfectly absorbing. Now, let us analyze the case when radiation incident on the surface at certain angle. This is the situation. You can observe here the radiation incident on the surface at angle theta. That means the direction of the radiation is making angle theta with the normal to the surface. Okay. And here we know the power incident on the surface, that is equal to IA cos theta. We have calculated this power relation, this P equal to IA cos theta, right. This is nothing but the formula of the same type as the calculation of the magnetic flux as well as electric flux. Now, linear momentum incident on the surface per unit time, it will be power divided by C. So, linear momentum incident small p divided by T equal to capital P divided by C. Okay. And we know capital P is IA cos theta. So, it is IA cos theta divided by C, right. Now, let us consider if surface is perfectly reflecting. If it is perfectly reflecting, that means angle of incident of ray should be equal to angle of reflection. So, let us make the diagram. You can observe this is the direction of the ray at angle theta with the normal. After reflection, because it is perfectly reflecting, the angle of reflection should be equal to angle of incident, like this. This angle will also be theta, and it is perfectly reflecting. That means total linear momentum will reflect back. Now, we can find the value of change in linear momentum. We know we can make the component of the linear momentum normal to the surface and parallel to the surface. Okay. And we know parallel to the surface there will be no change in the linear momentum, because there is no impulse parallel to the surface, but perpendicular surface linear momentum will change. We can make the diagram like making components here. This is the P cos theta normal to the surface, P sin theta parallel to the surface, and here after reflection we can make the component here also, and perpendicular component is P cos theta but in the upward direction, and this component will remain unchanged. That is why there is no change in the linear momentum parallel to the surface. That means total change in the linear momentum normal to the surface has the magnitude 2p cos theta, and we want to find the rate of change. That means dp by dt normal to the surface equal to 2ia cos theta divided by c, and we are interested in the vertical component, that means cos of this, right. So, it is nothing but 2ia cos square theta divided by c. Okay. So, this is the force exerted by radiation normal to the surface. Okay. Now, let us calculate the pressure. We can make the force component separately. So, this is the force applied by radiation in the normal direction, right, and these are the component of the force. This is normal to the surface and this is parallel to the surface. Okay. And we know there is no change in the linear momentum parallel to the surface, because this is P sin theta, this is also P sin theta. That means parallel to the surface this Fx will be 0, and this is equal to 2ia cos square theta divided by c. Okay. So, this is the force exerted by beam on in normal direction. Now, let us calculate the pressure. Pressure is equal to normal component of the force divided by area. This is the nothing but the normal component of the force, and this area is capital A. That means the pressure exerted by the radiation should be equal to 2I cos square theta divided by C. This is the radiation pressure when surface is perfectly reflecting. Let us analyze what happens when surface is absorbing. So, let us make the diagrammatical situation again. You can observe here radiation incident at angle theta with the normal, and after reflection 100% of the radiation is absorbed by this plate. That means final linear momentum equal to 0. So, in this case there is the change in linear momentum parallel to the surface as well as perpendicular to the surface. Okay. So, let us calculate the change in linear momentum per second in the normal direction first. So, initially you can observe the linear momentum in the normal direction p cos theta, and finally it is equal to 0. So, there will be one change. Instead of writing this 2 term, this should be equal to Ia cos square theta divided by C. So, we can write change in linear momentum in normal direction per unit time, that is equal to delta p by delta t in the normal direction, that is equal to Ia cos theta divided by C and cos theta, and this is nothing but, as we discussed, Ia cos square theta divided by C. But in the tangential direction or horizontal direction, we can observe here there is a change in the linear momentum because final linear momentum is equal to 0. That means dp by dt in the tangential direction equal to, this is the linear momentum total, and we are interested in the sine component. So, we can write dp by dt in the tangent direction equal to Ia cos theta divided by C multiplication sine theta, right. This force V will get Fx and this is Fy. So, this is Fx. This component will provide the shear parallel to the surface, and this component will be responsible for providing the pressure. If we want to calculate the pressure, what we will do? We will divide this expression with the area. So, radiation pressure in case of the perfectly absorbing equal to I cos square theta divided by C. Okay. So, up to this point, we learn how to calculate the radiation pressure. The radiation incident on the surface normal to the surface, also at certain angle. Surface may be perfectly reflecting or perfectly absorbing. Now, let us take few illustrations, and through coming illustration we will learn the application of the concept which we learn right now, right. So, let us take illustration number 1. In this illustration it is given the intensity of radiation of the sunlight. This is the incident intensity of the horizontal surface at sea level from sun is about 1 kilowatt per meter square. A part of the question it is given, assuming 50% of this intensity is reflected and 50% of the intensity is absorbed by the surface, determine the radiation pressure at the horizontal level, this horizontal level, and B part of the question it is given, find the ratio of the pressure, this pressure, that is the radiation pressure to the atmospheric pressure at the sea level, and this atmospheric pressure is given as 1 into 10 to the power 5 Pascal. So, let us move to the first part of the question. In first part of the question, we need to calculate the radiation pressure at the horizontal surface, this part, right. And we know pressure exerted by light, that is the absorbed light. We have learned this part, we know this pressure is equal to Ia divided by C. This is the force Ia divided by C, and pressure is force divided by area, that is I divided by C, right. So, this is the radiation pressure when radiation is absorbed 100%. But in our case, it is reflected 50% and absorbed by a surface 50%. That means the pressure exerted by the absorbed light should be 1 by 2 multiplication I divided by C. I is the intensity, C is the velocity of the light. Similarly, we can find the pressure exerted by the reflected light, right, and we have learned for this, should be equal to 2 I divided by C It is the case when 100% of the radiation is reflected back. But in our case, it is only 50%. That means we need to make 50% of this quantity, and this is equal to 1 by 2I divided by C. Right. Now, we can find the total radiation pressure on the surface, that is the summation of these two quantity. If we sum these two quantity, this will be equal to 3 by 2I divided by C. Right. This is the radiation pressure at the horizontal surface due to the sunlight or sun radiation. Now, we can find the value of P radiation, that is the radiation pressure, and we know the value of I, that is 1 kilowatt per meter square. We know the velocity of the light, that is 3 into 10 to the power 8 meter per second. So, let us substitute the value. 3 and 3 will get cancelled, and after calculation, this value is nothing but this is 1 by 2 into 10 to the power minus 5. So, this is 5 into 10 to the power minus 6 Pascal. This value. This is the answer to the first part of the question. Now, we need to find the ratio of the pressure, this pressure to the atmospheric pressure. Atmospheric pressure is given as 1 into 10 to the power 5 Pascal. So, this value divided by atmospheric pressure we need to calculate. So, let us calculate this ratio, and this ratio is nothing but this is 5 into 10 to the power minus 11. Right. This is the second part. Now, let us move to the next illustration. In this illustration, it is given a toy truck has dimension as shown in the figure. This dimension is A, this is B, and height of this cabin is H. And the width normal to the plane of this paper is small d. That means this dimension is small d. It is not shown in the screen because this is the two-dimensional view. This is a small d. That means the area of this surface, this one, this is A multiplication d. Similarly, the area of the top of the cabin, this one, is B multiplication d, and the area of this vertical face is H multiplication d. Okay. Now, let us move to the next part of the question. The sun rays incident on it as shown in the figure. You can observe the sun rays having intensity capital I incident on the truck at angle theta with the vertical. And we need to assume the all surfaces of the truck is perfectly absorbing. That is, no part of the radiation is reflecting back. We need to calculate the tension in the thread, this thread used to keep the truck stationary, and we need to neglect friction. Okay, this is the complete question. Let us first plan how to proceed the solution. Right. First of all, we have to calculate the power incident on the track. Step number 1, we need to calculate the total power incident on the track. In the second step, we need to find the momentum of the photon incident per second, right? And we know track is perfectly black. That means the final momentum reduced to 0 because all the photons are absorbed by the surface. That means final linear momentum will be 0. It means the rate of change of the momentum of the light is equal to the momentum of the photon incident per second, right? So, let us move to the first part, that is calculation of the power incident on the truck, right? So, let us calculate the area of the various part. First, let us take this surface. We know the area of the surface, this surface, as we discussed, this is A multiplication D. Area of this top of the cabin is B multiplication D. So, we can write here area of the top of the driving cabin is equal to B multiplication D, right? And we know the radiation is incident on this surface at certain angle, that is the theta with the normal. That means we can calculate the power incident of top of the cabin by the formula IA cos theta, and A we have calculated B multiplication D. That means power incident on top of the cabin is equal to I multiplication BD multiplication cos theta. This is the power incident at top of the cabin. Similarly, we can find the power incident on the rear horizontal part of the track. As we discussed, the area of this part is A multiplication D, intensity is capital I, and here also the angle from normal of the surface to the ray direction is again theta. So, the power incident on the rear horizontal part of the track is equal to I multiplication A multiplication D multiplication cos theta. Similarly, power incident on the vertical face, we can find this is capital I, that is the intensity, area as we discuss H multiplication D, and here the angle made by the direction of the ray with the normal is 90 minus theta. So, cos 90 minus theta will become sin theta. So, this is the power incident on the real vertical wall of the driving cabin, right. So, these are the power. Now, we need to calculate total power. That means, we need to add this part and this part to calculate the total power incident on the track. So, this is equal to summation of all three quantity. This is this one, right. We have taken I multiplication D as a common, I multiplication D common here, I multiplication D common here, and here also. Finally, we will get this relation, right. Now, we can find the linear momentum incident on the track per unit time. It is nothing but it is power divided by C. So, linear momentum, let us represent this quantity by small p, then small p divided by small t equal to capital P divided by C. So, this is the linear momentum incident on the track per unit time, right, this one. And we know this capital P equal to this value. So, we can substitute this value. So, this is the linear momentum incident on the track per unit time. As we discussed, all surface of the track is black or perfectly absorbing. That means, final momentum of the photon is 0. That means, change in the linear momentum will have the same magnitude, that is ID divided by C, and in bracket B cos theta plus A cos theta plus H sin theta. This will be nothing but force, right, but we are interested the horizontal component of the force, and horizontal component of the force will be equal to sine component of the force. We can make the free body diagram. This is the total force, this is the horizontal component, this is the vertical component, and we know vertical component F cos theta will be balanced by the ground normal reaction, and this will be going to balance by the tension force. So, this is the force F sin theta, and this is the tension force, right, horizontal component. So, this tension equal to F sin theta, this one is the tension. Now, we can substitute the value of F, this is the value of F. So, this is the final result, that is tension in the string connecting truck and this fixed point. Okay. Let us take one more illustration. In this illustration, it is given a plane light wave intensity capital I falls on a plane mirror surface area capital A with reflection coefficient rho. Reflection coefficient means fraction of the part of the radiation that is being reflected. This is given as rho. Okay. In next part of the question, it is given the angle of incident is theta, that is angle made by a ray with a normal to the surface is theta, and here we need to calculate the magnitude of the normal pressure exerted on the surface, right. So, let us do one thing, let us place the diagram to the next page here, right, and in question we are required to calculate the normal pressure. That means, we need to find the normal component of the force, that is the force exerted by radiation in the normal direction. Okay. So, let us find the momentum corresponding to the incident photon normal to the surface, that is vertically downward direction, right. And let us consider downward direction, that is the initial traveling direction of the photon in the downward direction as positive. That means, the linear momentum corresponding to the incident photon this will be equal to dp by dt, that should be equal to Ia divided by c cos square theta. We know this expression, we have calculated already, right. Now, we are giving the reflection coefficient as rho. If it is 100% reflection, that means the magnitude of the linear momentum in the vertical direction should have the same value, that is Ia divided by c cos square theta. But reflection coefficient is rho, that means the momentum of the reflected photon per second normal to the surface, that should be equal to dp by dt, that is equal to minus rho multiplication this value, right. We can rearrange this expression, we can write dp by dt, that is a reflected, that is equal to minus rho Ia divided by c cos square theta. For calculating the force, we need to find the rate of change of linear momentum. Here, rate of change of the momentum, that is the final momentum minus initial momentum, that will be the force in the normal direction. So, let us subtract this relation with this relation. So, this will be equal to Ia divided by c cos square theta will be the common, and in bracket we will have term rho plus 1, and overall sign will be negative, right. This is the rate of change of the linear momentum of the photon. And this is nothing but this is the force exerted by radiation on the surface, right. So, this is having the magnitude Fn, we will take the magnitude. So, this is the normal force, and for calculating the pressure equal to force divided by area. So, this value divided by capital A, that is the magnitude of this divided by capital A, will give the force exerted on the surface, this one. So, this is the radiation pressure due to the traveling of the photon, that will be in the downward direction, force in the downward direction because of the photon, and this is the pressure. Okay. You might have noticed up to this illustration that the magnitude of the intensity of radiation on the surface and the angle between the direction of radiation and normal to the surface was constant, right. You can observe in previous illustration, rays coming to the surface were parallel, right. That means the angle of incident of the rays with the normal was constant in throughout all illustrations. But in the coming illustration, the things are different. So, let us move to the next illustration. In this illustration, it is given an isotropic point source having radiation power capital P is located on axis of an ideal mirror plate. The distance between the source and the plate exceed radius of the plate eta times. That means the distance between the point source, S is a point source, and to the center of this plate is eta times capital R. Okay, and here we need to find the force of the light exert on the plate. Okay, so let us do one thing. Again, we need to place the diagram to the next page. Here, this is the situation, right? And this is the source. And here you can observe the distance of each and every point on the surface from the source is different. If you draw the lines, these lines are representing the direction of the ray. You can observe the distance of each and every point on the surface of the plate is different. That means the intensity at this point where rays are incident on the surface will be different. That means the intensity of the radiation is not constant over the surface. Also, you can observe the angle between the direction of the radiation and normal to the surface is not constant. You can observe here normal with normal, this angle is this, suppose this angle is theta 1, right, and suppose here the angle is theta 2, and here you can observe angle is 0 degree. That means each and every point the angle between the direction of the radiation and normal is different. That means this illustration is different from the previous illustrations. So here what we need to do? Here we need to use the method of integration. For this purpose, we need to explore a surface over which the intensity of the radiation may constant. So, let us explore the surface. Here we can do one thing. If we draw a ring like this of radius y and thickness dy, we can observe here each and every point on the ring is equal distance from the source. That means the magnitude of the intensity of the radiation is constant. First point. And second point, you can observe here the angle of inclination of the direction of the ray with a normal to the surface of the ring, because this ring will also have certain area. Say this area is dA. So, here we can observe the area vector dA and direction of the radiation motion is constant over this ring surface. Okay. So, it is better to take a ring of radius y and thickness dy, right. So, let us do one thing. Let us start a ray from S and incident on the ring surface, this one. Let this angle with the dotted line is theta, this angle is theta. That means we can say the incident photon are making angle theta with the dotted line. You can say this is also the axis of the disk. Okay. This is the normal. This one is the normal. That means this angle is also theta, because this is a mirror. That means the angle of incident should be equal to angle of reflection. That means the photon will reflect back like this, right. These are the reflected photons. That means this angle, if theta, this should also be theta. Okay. Now, we need to find the intensity magnitude over the ring surface. Let us take the distance of this point source to the ring is small r, right, and this is a point source. We can find the intensity by using the formula power divided by surface area. Here you can observe, if we take a sphere of radius r, we can say the intensity of the radiation will be constant over the sphere. That means power divided by 4 pi r square will give the intensity of the radiation at the ring position or ring surface, right. So, this is the intensity of the radiation over the ring surface, right. Now, let us calculate the linear momentum or momentum per second of the photon striking the ring per second. We know the formula for the constant angle and constant magnitude of the intensity. Here, let us consider this area as dA, this one, this area is dA. This is dA, and you know this angle is constant theta, and intensity of the radiation here is capital I. That means we can find the momentum incident on the ring surface, and let us consider the positive direction as rightward direction. That means dp by dt, that is the rate of change of the linear momentum, or you can say rate at which the linear momentum incident on the plate, that should be equal to I multiplied by dA divided by C and overall multiplied by cos square theta, right. This formula we have used already, right. This is the linear momentum incident on the plate surface per second, and which plate surface? The part of the ring. Okay. Now, because this is the mirror, that means this radiation will reflect back. That means it will move in the negative direction, because we have considered positive direction as rightward direction. That means the momentum per second reflected by plate, that should be equal to dp by dt, that equal to minus I divided by C dA cos square theta multiplied by rho, and rho you can say it is a reflection coefficient. So, momentum per second of the reflected photon, this one here you can observe this rho is a reflection coefficient. That means if it is 1, that means 100% of the radiation is reflected back, If rho value is 0, that means radiation is absorbed by the plate, okay, and negative sign is because radiation is reflected back. So this is the momentum per second reflected by the plate. Now we can find the change in momentum per second, change in linear momentum per second, or here you can say change in momentum per second. That should be equal to final momentum minus initial momentum. Final value is this, initial value is this. That means we need to subtract this to get the photon, that's the change of the momentum of the photons per second. So this is the diagram, and this is the intensity formula which we have calculated. And now let us write rate of change of the momentum of the photon incident on the plate, this one, right, this value final and this value is initial. Now we can take I divided by C and dA cos square theta and also minus sign as common. So this value will be equal to I divided by C dA rho plus 1 multiplication cos square theta, right. Magnitude of this will be the force exerted by radiation on this ring. This is dFn, and direction should be this one, rightward direction, okay. Now this plate is a mirror plate and it is reflecting 100% because it is not given, it is given only that it is mirror plate. So here we are considering that plate is reflecting 100% of the radiation. That means rho should be equal to 1. If rho is equal to 1, then magnitude of the force should be equal to 2I divided by C dA cos square theta, right. Now we can substitute the value of I. I is the intensity, that should be equal to P divided by 4 pi r square, and dA, that's the area of this ring, this should be equal to 2 pi y multiplied by dy. So let us substitute these values, okay. Now we need to integrate this function. So let us do one thing, let us write this expression to the next page. This is dFn, okay. Now we need to find the value of r and y, and we need to substitute the value of dy in term of theta. So let us do one thing, you can observe this is a right angle triangle here, this is the right angle triangle, and in this right angle triangle this value is y and this is L, and L equal to eta multiplication r. That means we can write here cos theta equal to L divided by R. So let us write cos theta equal to L divided by R. That means R equal to L divided by cos theta. We got the value of small r in term of theta and small l. Now we can write expression for the y. This is y, it is also unknown. This value is L. That means we can write tan theta equal to y divided by L. That means y equal to L tan theta, right. So here we can do one thing, we can find the value of dy also from this expression. We can write here dy equal to differentiation of this, L is a constant, and differentiation of the tan theta equal to sec square theta, and this is d theta. So we got the value of y, r and dy. Now we can substitute these value in this expression here. Now we can observe here some values may be cancelled out. This and this 4 pi will get cancelled, and here you can observe cos square theta is cancelled by sec square theta, right. This L square also get cancelled. So finally we are getting very simple relation, that is dFn equal to P divided by C, and here you can observe cos square theta multiplied by tan theta. So here we can write this is equal to P divided by C, right, and this is cos square theta multiplication tan theta and multiplication overall multiplication d theta. and we can write tan theta equal to sin theta divided by cos theta, and this cos theta will get cancelled. So here we can observe cos theta will get cancelled by this cos theta. Finally, we get the relation P divided by C, and this is sin theta multiplication cos theta multiplication d theta. Okay, so we can write the value of dfn, this one. Now finally we need to integrate with the proper limit. We can write this relation dfn equal to P divided by C sin theta cos theta multiplication d theta. We know the limit of theta. Limit of theta is here, you can observe this is 0 to this value. If I join this point to this point, that is the maximum angle made by the line joining the source, and the end point will be the maximum limit of the theta. Okay, so let us write this relation to the next page, this one. Right, we will use the substitution method of substitution for calculating this. Here we can write this relation. This is for the integration, and we can write here this is the integration, and this is the maximum value of theta naught about which we are talking about. So let us explore what should be this value. This is the diagram. If I join like this angle should be theta naught, and we can find the value of tan theta naught from this triangle, because we know this value and this value also, right? And here we will substitute sin theta equal to t. So let us do the substitution, sin theta equal to t, right? And here we can observe, let us set the limit. If theta equal to 0, t equal to 0, right? Lower limit of t is equal to 0. If sin theta, in sin theta, theta equal to theta naught, we can write here this t naught equal to, let us write the maximum value of t equal to t naught. So t naught equal to sin theta naught. This is the maximum limit, and from this triangle we can observe sin theta naught equal to r divided by this length, and this length is under root L square plus r square, and we know the value of L, eta multiplied by r. So this is the final relation, sin theta naught. Here we can substitute the value of sin theta equal to t, and limit we have calculated. So the integration will be like this, right? Here we can observe, if we differentiate this relation sin theta equal to t, this will be equal to cos theta d theta equal to dt. Now we can substitute respective value. The limit from 0 to t naught t dt, right? So integral of this t equal to t square divided by 2, right? We can substitute the limit. This is t naught square divided by 2 minus 0, right? Now we can substitute the value of t naught equal to sin theta naught. So this result will be equal to p divided by 2c sin square theta naught, and sin theta naught equal to 1 divided by under root 1 plus eta square. So after substituting this value, this is equal to p divided by 2c and multiplication 1 divided by 1 plus eta square. This is the final value. This is the force exerted by radiation on the plate. Okay.